Hello everyone, my name is Grea Fadillah. My name is 221011060077. I'm from Graph Theory Class B. Now, I want to explain my graph theory assignment. And because my name is end with 7, so I got a topic about Djikstra stardust path. Introduction. Nowadays, if you want to go to a place that has never been visited, you often search for the shortest path to the place you want to visit. This shortest path search is done in order to save travel time and costs. In searching for the shortest path, you can use a method that is used to find the shortest path. This method is called the Djikstra algorithm. Dijkstra's algorithm is an algorithm used to find the shortest path in a directed graph. This algorithm was discovered by Edgar Y.B. Djikstra in 1956 and published in 1959 in a journal entitled A Note on Two Problems in Connection with Graphs. In brief, the workings of this algorithm start from determining one node that will be used as an initial source. Then, from the initial node, the shortest path is searched by comparing one edge with another edge and also not forgetting to add the value of the previous edge with the edge after it to see which shortest distance comparison will be used. This paper will discuss the theory, review the literature on the Djikstra algorithm, and the application of the Djikstra algorithm in everyday life. Next is literature review. History and development of Dijkstra's algorithm. Edgar Djikstra is a Dutch computer scientist who was born on May 11, 1930 in Rotterdam, Netherlands. He developed the structured programming paradigm for writing computer programs. Djikstra is known for discovering the shortest path algorithm in a directed graph. Graphs are used to represent discrete objects and the relationship between them. Visually, an object in a graph is represented by a point, and a relationship between objects is represented by a line connecting the 2 points. In its development, the development of Dijkstra's algorithm continued. In 1962, George Danzig and Edgar Djikstra developed a variant of Dijkstra's algorithm that can handle negative weights by detecting negative cycles. This variant is known as the Djikstra-Danzig algorithm. Since its invention, Dijkstra's algorithm has become one of the most widely used algorithms in various fields. It is also the basis for the development of other algorithms such as the A-star algorithm used in heuristic pathfinding. To date, Dijkstra's algorithm continues to be a topic of research and development. Various enhancements and optimizations have been proposed to improve its performance in certain cases or to suit specific application needs. In the modern computing era, Dijkstra's algorithm remains a very important and influential algorithm in the field of computer science and graph theory. Next is basic principles and how Dijkstra's algorithm works. Dijkstra's algorithm is based on the principle of the greedy algorithm. The way this algorithm works is by visiting all nodes and creating the distance. If there are two nodes with the same distance, the distance with the lowest weight is chosen, so that all nodes have an optimal distance and this search is carried out until the destination node is found. Thus, Dijkstra's algorithm ensures that every time it selects a node, it is the node with the closest distance from the unvisited source. This algorithm will definitely find the shortest path from the source to all other nodes in the graph. Research on optimization and algorithm applications. Some research on optimization and application of Dijkstra's algorithm, namely, first is shortest route search for tourist attractions in Bali using Dijkstra algorithm. This research is the result of the development of the source root search system for tourist attractions in Bali using the Djikstra algorithm. The resulting system is a web-based geographic information system with PHP script and MySQL as the database. With this system, visitors can find out the source route to a place in Bali. Second is development of geographic information system for blood donors using Android-based Djikstra algorithm. In this research, a system is designed that can find blood donors in Bandar Lampung by using geolocation technology and Djikstra algorithm to determine the closest route. The output produced in this research is a blood donor search system based on the nearest location and a system that can be installed on an Android-based smartphone. Next is applications. Dijkstra's algorithm is most commonly used in navigation and mapping systems. For example, to find the shortest or fastest path between two locations by considering factors such as distance, travel time, traffic conditions, and others. Another example, Dijkstra's algorithm can also be used in first, computer networks and telecommunications. Dijkstra's algorithm can be used to find the best routing path between two nodes in the network. Second, vehicle routing in logistics and transportation. This algorithm can perform the shortest or the cheapest route in vehicle routing. Electricity network analysis. Dijkstra's algorithm can be used to find the shortest and cheapest path in the installation or maintenance of electricity network infrastructure. In real-world applications, Dijkstra's algorithm has several advantages and disadvantages. Some of the advantages and disadvantages of the Dijkstra algorithm are as follows. For the advantages, the first is accuracy. Dijkstra's algorithm can guarantee accuracy in finding the shortest path between two nodes on a positive weight graph. Efficiency. This algorithm is efficient enough to be implemented in the real world, especially with the use of prioritized data structures such as Fibonacci heap or binary heap. Flexibility. Dijkstra's algorithm can be applied to mapping, computer networks, and project planning. It can be adapted by modeling the problem as a weighted graph. And for the disadvantages are, first is negative weights. Dijkstra's algorithm can only be applied to graphs with positive or zero weights. If negative weights are present, the algorithm cannot guarantee to find the shortest path correctly. Dynamic changes. In cases where the graph changes dynamically, such as changing weights or adding nodes, this algorithm must perform the calculation from scratch to get accurate results. Scale problem. For very large graphs or millions or more nodes and edges, Dijkstra's algorithm becomes less efficient as its time complexity depends on the number of nodes and edges. Next is discussions. Comparison of Dijkstra algorithm shortest path with other algorithms. Dijkstra algorithm is the most popular algorithm in solving the shortest path problem in non-negative weighted graph. However, there are also several other algorithms that can solve the same problem of finding the shortest distance. These algorithms are: first is Bellman-Ford algorithm. Is one of the alternatives to Dijkstra's algorithm. The main advantage of Bellman-Ford is its ability to handle negative weights on graph edges, while Dijkstra can only handle non-negative weights. However, Bellman-Ford's time complexity is lower than Dijkstra for the general case, making it less efficient for non-negative weight graph. Second, the A-star algorithm is a heuristic search algorithm that can be a faster alternative to Dijkstra in many cases, especially if a good heuristic function is available. However, A-star cannot guarantee finding the shortest path if the heuristic function does not meet certain conditions. A-star is more suitable for path finding in environments such as games or mapping, where heuristics can be used effectively. Third is Floyd-Warshall algorithm. It's used to find shortest path between all pairs of nodes in a graph, although it has a higher time complexity. It can be useful in some applications that require a matrix of shortest distance between all pairs of nodes. However, Floyd-Warshall becomes efficient for large graphs. And directed acyclic graph or DAG algorithm, a topology sorting algorithm that can be used to find shortest path with efficient time complexity. However, this algorithm is only applicable to the edges and cannot handle graph with cycles. In navigation and mapping system, Dijkstra's algorithm remains the top choice due to its efficiency in finding shortest path on non-negative weight graph. However, the selection of an appropriate algorithm also depends on the graph characteristics, the availability of heuristics, or the needs of a particular application. Next is possible improvements or optimizations to Dijkstra's algorithm. One of the optimizations that can be done on Dijkstra's algorithm is to make use of more efficient prioritized data structures such as the Fibonacci heap. This can reduce the average time complexity. In addition, pruning techniques can also be used, which are applied to remove irrelevant nodes or edges, thus improving efficiency especially for large graphs. In graphs with very large size, parallel implementation of Dijkstra's algorithm on distributed system or parallel computing can be a good solution. The algorithm can also be modified to handle pathfinding under certain constraints, such as time or cost constraints, by adjusting edge weights and evaluation function. A bidirectional approach, where the search is performed from the source and destination simultaneously, can save search time. In addition, Dijkstra's algorithm can also be combined with other algorithms such as A* or other heuristic algorithms to form a hybrid algorithm that utilizes the advantages of each algorithm. In cases where the graph does not change dynamically, pre-processing can be performed to speed up the shortest path search by performing preliminary calculation on static part of the graph. These enhancements and optimizations aim to improve the performance of Dijkstra's algorithm in certain cases, such as large graph, sparse graph, or pathfinding with constraints. The choice of appropriate optimization depends on the problem characteristic and research constraints. Limitations and challenges in implementing Dijkstra's algorithm. Besides the advantages and disadvantages, Dijkstra algorithm also has some limitations and challenges. For example, in implementing Dijkstra algorithm on system with limited research, such as mobile or embedded device, memory usage can be an issue. The algorithm requires storing information about all nodes and edges in the graph, which can strain limited memory resources. Another example, Dijkstra algorithm requires global information about the entire graph, including the weights of all edges. In some situations, this information may not always be available or difficult to obtain, which poses a challenge in implementing this algorithm effectively. Despite some limitations and challenges, Dijkstra's algorithm remains one of the most widely used and effective algorithms for solving shortest path problems in various real applications. By considering these limitations and challenges, developers can choose alternative optimizations or algorithms that are more suitable for specific cases. Conclusion: Dijkstra's algorithm is one of the most important and influential algorithms in the field of computer science and graph theory. It is used to find the shortest or most optimal path between two nodes in a weighted graph. Since its discovery in 1959, Dijkstra's algorithm has undergone various developments and optimizations, and is widely applied in various fields such as navigation and mapping system, computer networks, vehicle routing, social network analysis, and project planning. Dijkstra's algorithm has advantages in terms of accuracy, efficiency, flexibility, and ease of implementation. However, it also has limitations, such as not being able to handle negative weights, difficulty in handling dynamic changes in the graph, scaling issues for very large graph, and the need for global information about the entire graph. In the implementation of Dijkstra algorithm, there are several possible improvements or optimizations that can be done, such as the use of more efficient priority data structures, pruning techniques, parallel implementation, handling search constraints, bidirectional approaches, hybrid algorithms, and pre-processing. These optimizations aim to improve the performance of the algorithm in certain cases, such as sparse graph of large size, or pathfinding with constraints. Despite its limitations and challenges, Dijkstra algorithm remains a popular and effective choice for solving source path problems in real applications. It is also the basis for the development of other algorithms such as A** and other heuristic algorithms. By considering the advantages, disadvantages, and characteristics of the problem, developers can choose the most suitable algorithm implementation for a particular case. Thank you.